In this video, we are going to start learning about torque, and to begin with, we're going to give it the full calculus treatment. There'll be a video after this where we do some torque with no calculus, but torque is, as we've mentioned in some previous videos, the symbol for torque is a Greek tau. It's spelled like this, T-O-R-Q-U-E. You can think of this as a rotational force. First of all, let me say that that's not a thing. A force is a vector, which means it acts in a line. But a torque takes into account that a force is acting on a three-dimensional object. Therefore, where you apply the force makes a difference to the subsequent rotation. So the torque takes into account a force and the geometry of the object to which you're applying the force. It produces, or it tends to produce, a rotational acceleration. Just like a force tends to produce a linear acceleration, a torque will tend to produce a rotational acceleration. All right, so what are we going to do with this? Well, first let's see how to calculate it. Let me give you the definition. Number one, I would say that torque is a vector. So I'm going to frequently leave off the vector symbols, we all do, but it is technically a vector, and it is calculated thus: R cross F. Now, let me say, if you don't know what a cross product is, there are some videos on this playlist about how to calculate a cross product and what it means. So I would encourage you to stop this video, go watch the cross products, because the cross product videos, because we're going to need to understand what it means to proceed. So if you haven't watched those, go watch them and come back. I'm going to assume that you have watched them, that you do know what a cross product is. So we'll talk about what these vectors actually are. Say I have some sort of object. Let's just make it simple, like a bar. And let's say that I'm going to apply a force that looks like this. Here's my applied force. Now, when I'm going to calculate a torque, it's no longer good enough to just say it's this force and that's it, right? We've talked about how we need to take the geometry into account. But if I take the geometry into account, you immediately have to say, well, about which point on this bar, or actually outside of this bar, anywhere in the universe, about which point are you going to calculate the torque? That might make a little bit more sense as we do some examples, but let me just say this. I can calculate the torque about any point. If this thing is pinned so that it is going to rotate about a hinge, it might make sense to calculate the torque about that point. If it's not, it might make sense to calculate the torque about its center of mass, because if you apply this force to a freestanding object, it will begin to rotate about its center of mass. Those might be some clever points, but I can actually calculate the torque about any point in the universe. So let me pick one. I'm going to pick the extreme end of the bar over here. I might pin it down so it has to rotate here. I might not. It doesn't really matter. I'm going to calculate the torque about that point. So now I have F. What R is now is a displacement vector pointing from the point that I've chosen to sum the torques about to the point of application of the force. And I'm going to assume that this bar is thin enough to where I don't have to worry about angling this down at all. It's just the force is applied here. That vector goes from this point about which I'm summing to this point, and that's the vector R. And of course, the force should be a vector as well. So that's what R and F are. If I'm actually going to calculate this torque, what I need to do is redraw these vectors tail to tail. Remember, you can move a vector anywhere you want to as long as you don't change its length or its orientation. Now, when I do that, there is some angle here between R and F. And you might be tempted to say there's an angle between F and R, but we're going to have to be careful with that. So let's say I'm going to pick a number let's say that this angle is 30 degrees. I don't normally pick numbers here. I would just call that a theta, but I need a number, and you'll see why in a second. So this is 30 degrees. Notice if I'm moving from R to F, I'm rotating through that angle, from R to F. And that actually turns out to be important, because if I'm calculating the torque as R cross F, just a reminder of what the cross product means, it's magnitude of R, should be just a normal vector, times magnitude of F times the sine of the angle between them. And then there's a normal vector. We'll talk about the normal vector in a second too, but right now let's talk about this sine of the angle between them. That angle is measured. If you're going to use this definition of the cross product, that really looks like a P, should be an F. If you're going to use this definition, this angle is really specifically measured. It is measured from R to F counterclockwise. Okay, let me say that again. From R to F counterclockwise. By convention, we choose the counterclockwise method. So what does that mean? Well, if I'm going to calculate this, then the magnitude of the cross product is going to be F. I should not do it that way. I should do R. Magnitude R times magnitude of F times the sine of 30 degrees, and we'll deal with this normal vector in just a second. We're going to come back and put in the normal vector on this expression and talk about what it means. But first of all, let's talk about the sine of 30 degrees, right? What is the sine of 30 degrees? Well, the sine of 30 degrees is 1/2. Fair enough. So this turns out to be, well, I'm going to leave it like this. The sine of 30 degrees is positive 1/2. I think we can all remember that. Okay, fair enough. Now, what if the force that I applied did not look like this? Let me redraw the system and give you a different force. There is my force. And I will say that this is also 30 degrees. And I'm again going to sum the torque, or calculate the torque about this point, which gives me an R vector that looks like that. So far it looks pretty similar, but we're about to see a difference. If I now, sorry, this is R. If I now rearrange my vectors so that I can do the definition of the cross product, they look like this. There's R, and there's F. I just put them tail to tail, and there is my 30 degrees. Okay. Now, if R and F are the same, you might be tempted to look at this and say, well, the torques have got to be the same. But remember how we defined this theta. We measure from R to F moving counterclockwise. And so if I'm going to calculate the torque of this one, R cross F, I've got the magnitude of R times the magnitude of F times the sine of, well, if I have to go from R to F, that is all the way around the horn, right? Going from R to F counterclockwise. That turns out to be the sine of 330 degrees. And what is the sine of 330 degrees? It's negative 1/2. The sine of 30 is positive 1/2. The sine of 330 is negative 1/2. So there is the difference. The torque, this torque is positive. This torque turns out to be negative. That's a big deal. Torque is, as a cross product, is not commutative. The cross product is one of the ways which we multiply vectors. It is not commutative. All right, so now that we've seen that, let's talk about this normal vector. The cross product results in a vector which is perpendicular to the plane formed by these two vectors. Any two vectors define a plane. In this case, R and F define the plane of this sheet of paper. Same here, R and F define the plane of the sheet of paper. They define it because they're in the plane. So if I'm going to have a vector that is normal to the plane, that means it's either going to have to come up out of the page or go down into the page. It's either going to come up the positive z-axis or down the negative z-axis. To think about what this means, this is the torque vector. To think about what that means, you can imagine that wherever you're calculating the torque about, if this object were to rotate about that point, I'm not saying it does rotate about it, I'm saying if it were to rotate about that point, the torque vector would lie along the axis of rotation. It would be collinear with the axis of rotation. Which direction it points depends on if it's positive or negative. By convention, we take up out of the page to be the positive z-axis, and we take into the page to be the negative z-axis. You can relate that to these two by looking at the actual system. If this force would tend to cause a counterclockwise rotation about this point, we say that it is positive torque. If this force tends to cause a clockwise rotation about this point, we call it a negative torque. Again, I'm not saying that it does cause a rotation. I'm saying if nothing else were acting and you were letting this thing rotate about this point, what would the motion look like? This is determinable by the right-hand rule, which, again, if you don't know what that is, go watch some videos that I've made previous videos on this playlist. Right-hand rule here is going to say stick my fingers in the direction of R, the first vector. Put my fingers in the direction of R. Sorry about the shadow. I'm trying to do something about it. Curl them towards F, right? Fingers in the direction of the first vector. Curl them towards the second vector. Stick up your thumb. That's the direction of the resultant vector. So in this case, the vector comes up out of the page. The symbol for that is this. It looks like the tip of an arrow coming at you. Right? If I were to draw this a little differently, in a plane, there's F, there's R, and then the torque is coming up out of the plane. I don't know if that makes it better or worse. F and R lie in a plane, and torque is up the z-axis. In this case, do the right-hand rule again. Fingers in the direction of R, curl them into F, stick out your thumb. I get a vector going into the page. So that we draw like this. Looks like the backside of an arrow going away from you. So that is the full calculus treatment of torque. You've got to do the cross product. And I should say that if you're given R and F in IJK format, or some unit vector format, you might not use IJs and Ks, you might use X hats, Y hats, and Z hats. But if you're given these vectors in that form, usually the explicit calculation of the cross product represents the most straightforward way to get at the answer. But if you're not, if you're given something like this, and I guess to be complete here, there should be a 30 degrees there. If you're given something like this or this, I feel like not using calculus to get at the torque is probably more straightforward. So in the next video, we're going to talk about how to calculate a torque without calculus, and I hope we're going to come to some intuitive understanding of what torque means. So in preparation for that, the last thing I will say about this is to talk generally about the cross product and what it does. And to do that, I'm going to remind you what the dot product does, the other way we multiply vectors. The dot product serves to pick off parallel components. If I have formed R dot F, that would tell you how much of R was in the direction of F, or alternatively, how much of F is in the direction of R. It picks off parallel components. The cross product, because of this sine function here, whereas the dot product had the cosine, the cross product actually picks off perpendicular components. It picks off how much of F is perpendicular to R, or I should say how much of R is perpendicular to F, although we'll see that it can work both ways. So those are one of the functions of the vector multiplications, is to pick off particular components. The dot product picks off Parallel components, we call it a projection. The cross product picks off perpendicular components, and that's going to become important.